Eclipse Mega Movie by Anthony, Christian, and Raul. Introduction. Inspired by a Kaggle competition titled Categorizing Solar Eclipse Phases, the competition was founded by NASA's Eclipse Mega Movie, created to discover the secret lives of solar jets and plumes. Next step in the process, ensure that the data can be quickly organized and has the correct information associated with each image. That's where we come in. Goal. The goal of this project was to identify the different phases of the eclipse and categorize either as total solar eclipse, a partial eclipse, or not an eclipse, with a total amount of either of 8 categories, as shown below. Dataset. We had 495 training images, 495 training labels, 140 testing images. The training images and the testing images both had the format as shown in the bottom left. The training labels followed the same format as the training and the test labels followed the same format as the image on the bottom right, where the image ID was mapped to the image or the training and the testing IDs in the image files, and the labels had the respected label categories. At the top right, you can see the distribution of the images itself in the training file with 187 total eclipse.
Categorizing images. Images for the trained data were labeled, but the images for our test data were unlabeled, so our first step was to manually label the test images. We ran a script to output each image from the test folder so that we could determine what to label that specific image. For example, this image popped up and we labeled it 2 since it's about in the 26 to 55% range for the eclipse. And our approaches for this project were CNN with pre-trained model with layers removed, SIF plus bag of visual words plus support vector machine, and SIF plus bag of visual words plus logistic regression. Before we talk about the first part of the project, let me describe what a CNN is. A convolutional neural network is an artificial neural network that is used for image recognition and can detect and extract features within an image. These features are then used for things such as object detection or classification. We also used various learning algorithms alongside our CNN, such as logistic regression, which is a classification technique used to predict the probability for a specific class for certain data. It's usually used for binary classification. Support vector machine is used for image classification and regression. A boundary known as the hyperplane is used to separate the data into different classes while maximizing the margin between classes. And k-nearest neighbor, which is used to classify data based on what is near it. The data is classified based on the number used for k and the amount of k neighbors around the data. And our custom model. Our custom model consists of transfer learning, where a CNN is pre-trained on a specific dataset in order to improve performance on a different dataset. In our case, we trained our CNN on ImageNet. We also included fine-tuning in order to freeze all layers to prevent weights from changing, but unfreeze a certain amount of layers in order to update those specific layer weights. Our CNN process. We would test the CNN by running it with different CNNs, such as MobileNet v2, ResNet 50, and EfficientNet B0, and pre-train it on ImageNet. We would then keep a certain number of layers of the CNN in order to prevent overfitting. We add global average pooling to get a flat feature vector from convolutional maps. All layers are frozen and then a certain amount get unfrozen. Features are extracted from the frozen CNN and normalized in order to be used for SVM, KNN, and logistic regression. Data augmentation is performed to prevent overfitting and improve generalization. We then use a model with fine-tuning and compile with a low learning rate. Various parameters are changed when testing, such as the amount of layers to freeze and unfreeze, data augmentation parameters, image size, etc. This helped improve results significantly, with our best result from using ResNet 50 with our custom model, which gave us 95.71% and with only 6 misclassified images.
Now to talk about the second and third approach for this project, we use SIFT plus bag of visual words and then pass that on to support vector machine and logistic regression. We started off by pre-processing all the images. We resized them all to 256 by 256. This normalizes the number of key points and prevents dominance by larger images, pretty much balancing out the outputs. We then applied Gaussian blur to get rid of noise in images that cause unwanted key points and descriptors. We can see in the first image kind of how Gaussian blur works. Each pixel is being adjusted depending on the pixels around it and how far they are from the center pixel. Closer neighbors to the center pixel are given more weight, which is more influence. Farther neighbors are given less weight, and these weights actually come from the Gaussian function, which looks like a smooth bell curve. And then we convert the image to grayscale, since SIFT only looks for gradients of intensity and helps reduce computational cost. If this were a red, green, and blue RGB image, it would take 3 times longer to process. We then use Clocky, which is contrast limited adaptive histogram equalization, to enhance local contrast to make edges, corners, and textures more pronounced. We can see from the second image kind of how Clocky works. It takes an image, breaks it into 4 tiles. Each tile has a histogram, and then we choose a clip limit to cut off the histogram at. Then the top excess is actually redistributed to the rest of the histogram, and in return we get an image with better contrast. No dark and no light colors are dominating the actual image. And then in the last image we can see it before and after pre-processing. In step 2, we classify flats and darks because we were having issues when running these through SIFT, as we were either getting no key points, or if we did get key points at the end, they were being classified as something other than dark or flat. So we use the image histograms and statistical thresholds. For dark image histogram, most of the peaks are going to be towards the value of 0 because that is black. And then for a bright or flat image histogram, most of the peaks are going to be towards the value of 255, which is white. For statistical thresholds, we use the mean intensity, which is the average brightness of all pixels. We use also the standard intensity, which is how much brightness varies, like the contrast and the texture of the image, and also the dominant pixel, which is the most common pixel value in the histogram, which is the highest peak on the histogram. To classify an image as dark, we had to have a mean intensity of less than 25, a standard intensity of less than 6, and a dominant pixel value of less than 20. And to classify an image as flat, we had to have a mean intensity of greater than 80, a standard intensity of less than 8, and a dominant pixel value of greater than 50. These are numbers that we picked and we messed around with, but these can be adjusted as well. And then we pass the rest of the images back to be processed through SIFT and bag of visual words, and then run those through SVM, support vector machine, and LR, logistic regression. In step 3, we use SIFT to extract key points and descriptors from each image. Key points are distinctive patterns found, like corners, edges, or blobs, which are used to create the descriptors. Descriptors are 128 dimensional vectors used for matching features between images. In the bottom, we can kind of see the process of creating these descriptors. We first start off with the key points on an image. They're resized to 16 by 16 and then divided into 16 4x4 pixel squares. Each 4x4 pixel square has 8 gradient directions, and each 4x4 square gives us a gradient direction histogram over 8 directions, which then gives us the whole vector of 128 dimensions. And then on the bottom you can kind of see how each 4x4 with 8 directions is concatenated into the 128 dimensional vector. The vector is then passed on to step 4, where we use k-means to build a vocabulary for the normal images. K-means group similar SIFT descriptors into a certain amount of visual words, and visual words are like image features but clusters of similar low-level features or of similar descriptors. In figure 1, we can see that before k-means we have these descriptors that are scattered around on the chart. They seem like they can be grouped together, but they're not. That's where k-means comes into play. It groups the similar ones together. It creates these clusters, which are the actual visual words. We have a more brief, vague description in figure 2, where we take an object, which is an image of a person, and then we create a bag of words where the words are features of the image of the person. In this project, we chose a vocab size of 300. This means we get 300 visual words out of the k-means. Visual words are then used to create a bag of visual words histogram, which is a fixed size vector. This size for us is going to be 300 because we have 300 visual words. This is then used as the input to a machine learning model, such as the support vector machine or logistic regression. In step 5, we normalize the normal images using standard scalar, which ensures all features contribute equally and improves performance of models. In step 6, we train the classifier, whether it's SVM or LR. First, we start off with using grid search to find the best parameters for each model. Grid search pretty much uses a different combination of values and algorithms to figure out what is the best combination to use for the model depending on the training images that are being passed through it. It holds on to the best parameters so that it can be used for testing. And then we run the normal scaled images through each model. And then lastly, we test. We run the normal test images through each model for predictions using the best parameters that were found through grid search. And then we find out how our model does. And here are the results of using SIFT and bag of visual words. For SVM, we got an accuracy of 78.57%. And for LR, we got an accuracy of 76.43%. On the bottom of each confusion matrix, we can see the classification report, which holds the values for precision, recall, F1 score, and support of each class. For precision, it is the correct positives out of predicted positives. We can take a look at the SVM confusion matrix on the left. This value comes from the values in the columns. 48 were predicted correctly as a full eclipse. 1 was misclassified. A 3 was misclassified as a 0. 3 that are labeled 5 were misclassified as a 0. And then for recall, we have correct positives out of actual positives. We can look at the rows for this value. We have a support of 51 for a full eclipse. 48 of those were correctly classified, and then 3 of them were misclassified. They were misclassified as a 4. With the F1 score, we can combine both of these values and calculate the harmonic mean of precision and recall, which balances the precision and recall, like I said. And then the support is the how many images were in each class. So for this model, the best performer was a label 0, which is a full eclipse, which had the highest F1 score. And then the worst performer was a label 3, which was 56 to 95% eclipse, which had the lowest F1 score. The reason I chose to focus on the F1 score for the best and worst performer is, like I said earlier, it combines both the precision and the recall, so it takes more into account.
Discussion of results. CNN versus bag of visual words. CNN can learn directly from raw images, learning hierarchical features starting from low level, like edges, to high level, like shapes, textures, patterns, and colors. Spatial data. Unlike bag of visual words, who treats images as a collection of words, CNN uses the raw data instead of histograms. They can leverage spatial hierarchies and local contexts. Bag of visual words uses handcrafted features, struggles to find important tasks, relevant features. Performs poorly on data class variability, like different lighting or viewpoints, due to their inadaptability. Bag of visual words, in addition, can lose important fine-grained details during quantization and disregard spatial layouts. Discussion of results. Bag of visual words did a good job classifying classes like full eclipse and 26 to 55%, which have good quality features as shown below, where you can see that the SIF was able to get features that really describe what the image is. However, because SIF, 2 classes had a hard time getting classified, which were darks and flats. Due to them not having any features, this required us to use thresholding, which further complicated the pipeline. This was another pro with CNN, because CNN was able to do this out the box instead of having to pipeline with using thresholding. As mentioned above, bag of visual words perform well on images with distinct and reliable key features. However, due to the high variability within this class, such as images being cloudy, dim, or bright, bag of visual words wasn't able to capture features that truly mattered for generalizing across the images. This need for more robust features extraction highlights the reason why CNN was able to outperform bag of visual words. As you can see on the right, this image of a person is not a solar eclipse. Obviously, SIF will be able to get features that would tell it that this obviously is an eclipse. But for not a solar eclipse on the right, where it you can see that there is a solar eclipse, it would still get features there that were more resembling of an eclipse than something that was in the not solar eclipse file or image set. And as you can see here, you can just see the total amount of misclassifications with the sift and bag of visual approach. You can just see how much more they would get, since we got 30 misclassification images with the SVM and 33 misclassification images for LR or logistical regression, while CNN only ended up getting 6 misclassifications. And as you can see at the bottom, they would get um, more missed images with darker images that were just not able to really be classified through the sift approach itself, and had to use thresholding. A lot of the manually mislabeled tests, a lot of images were mislabeled test images, as we were given unlabeled test images, so we had to use to do our best guess. Some images of the eclipse are very dark, classifying as dark images. Different percentage eclipse images have fairly the same kind of key points, making them look alike.